And then I'll talk about what's been done so far and composition under information-theoretic privacy and interaction, as well as what does that really mean for inference, this kind of metric, and sort of wind it up with some kinds of comparison of IT privacy and DP. That's not a fair comparison, but we'll try something. Okay, so everybody here knows about privacy. I'm not sure I need to say it. But compared to when Delaney started looking at this problem, and today, we just have a number of realms, electronic realms, where data is being collected. Data is it's not just the census, the government, every retailer, everybody collects data about you. There's also this interaction between enterprises that nobody's really worrying about. It happens all the time. Power systems, where I also work, my other avatar, there's a huge restriction of data sharing because they don't trust each other due to both security and privacy reasons. And so it's not clear that one size fits all. It's not clear what should be the appropriate mechanisms for different applications. And so a question that I want you to leave you with is identity the only kind of privacy one should worry about? Is there a notion of, say, feature identification? Maybe I know somebody's identity, but I learn more from that data that they're pregnant. So it's more about feature identification, and maybe this is maybe information theoretic metrics could be used there. Okay. So very simply, the information theoretic model is as follows. You have a data set. It's generated from some underlying distribution. The data set has two parts to it, public and private. So throughout my talk, X is public, blue, and Y is private, red. And what you want to do is to map X to some X hat through a mechanism, which is obviously a randomized mechanism. And your goal is to identify appropriate privacy and utility metrics. So, information theory, the two big problems in information theory are, how to compress data and how to transmit data without errors. And in both those problems, mutual information sort of comes out of the problem as a solution. But when it comes to security and privacy, we do not have that beautiful solution, and we sort of impose a metric for security and privacy. Mutual information is one of the oldest metrics. Shannon used it, but in the perfect secrecy case, and then Weiner introduced it for any arbitrary levels of secrecy. So it sort of is a tradition. It's not clear it's the best, but it is a metric. And so the goal here is to say, let's take mutual information as the metric for leakage of the private data from what's revealed, X hat, so mutual information Y and X hat, and it's subject to a constraint on utility, which we measure through distortion. How much is your data different from what it was? How much is X hat different from X? And everything is on average because we assume we know source statistics, okay? So many common utility metrics could be Hamming, quadratic, log loss, as in learning examples, and in the broad class of F divergences.
What do you mean by assuming all the source statistics?
Assuming source statistics. So I assume that I have knowledge, or I can empirically compute the statistics of the data sets. Exactly. The joint distribution of the public and the private. I may not know the private, but I have some estimate of the joint distribution.
So I'm a little confused. So you're trying to minimize the distance between X and X hat. X is public.
Yes.
No, what?
X is a.
What I know is the joint. So X itself might leak information about Y, and now I want to reveal
Exactly.
something close to X that reveals less about Y.
Right. So the simplest way, the simplest model in say DP is where you just have X. It's your data set.
X and Y are the same thing.
Exactly.
Right.
So here we sort of separate it out. X could be recommendations and or what movie they watch, and Y could be their underlying political preferences. Right? So it's a larger class of inference models in that sense. Okay, so what I want you to take away is that if you look at this mutual information between Y and X hat, it's really the Kale divergence of the posterior relative to the prior of your private data. So this is again in contrast to DP, where you're looking at your mechanism and the ratio of mechanisms. Really what you're doing here is you're trying to minimize the amount you can infer about the private data, given what you're revealed, versus how it should be as close as possible to the original inference you could have made without any information revealed to you. Okay? So the distribution after, this should be after observing x hat, should be as close as possible to the prior distribution on y. Okay? So you could also have more general models where I reveal functions of x and then I hide functions of y. Okay. All right. So this is your basic model. This model x and y here are random variables. They could be random vectors, meaning it could be a database of length, a data set of length n. Okay, so everybody knows this as well. You know, people have looked at privacy in the statistics literature, data mining literature, database, and so on. And everybody here knows about this very compelling formal framework of differential privacy. And the focus there is on non-identification. Okay, so information-theoretic privacy, in contrast, it acknowledges the fact that data has some underlying statistics, so it provides average case, on average guarantees on the data, and it is really computation independent in that sense. Yeah. Okay, all right. Okay, I'll take that offline, but bear with me as I go through the rest. Okay, so but the point here I want to make is that maybe you even know the people in the database, and the goal is to go beyond identification to look at leakage of private features from the public data, the data that you have access to. So there could be some other models or requirements of your data set. So here's your formal model. I have a database of length n, and I write it in this notation xn. And it's a very simple example here. What I'm looking at is categorical data, such as social security numbers, zip codes, etc. And in this simple problem, I say the public is equal to the private, so there's no distinction. And so you have an n-length data set, xn, and you assume it comes from an IID source. So there's just this px that you have to worry about. What I'm interested in is designing a n-length privacy mechanism that's really this block mechanism that maps x to x hat n.
So just to understand here, n means xi is
Generated from, pardon?
is generated from one separate individual.
Yes. Each xi represents data for a separate individual, yes. So it's a data set for n individuals, but you're assuming they're all identically distributed without loss of generality. Okay? But you know, every sample could have a different probability in the distribution. Okay, so, and it's categorical data. Your output set is very similar to your input set, right? I'm not going to add noise and change social security numbers and zip codes to some real value. Okay, so what is a metric here for utility? I say it's the Hamming metric, Hamming distance. In other words, there is a cost to changing your data. That's unit cost, unit penalty, and there's no cost if you do not change the data. That's effectively equivalent on average to saying the probability that what you reveal is not equal to what the original data set was should be bounded by some requirement D. Okay, all right, so what does this tell you? If you take the optimization problem, what do you want to do? You want to minimize leakage subject to a distortion constraint, yes, Anand?
Just going back for another way of phrasing, you're saying for 1 minus d fraction of the individual surface for the
Yes. Yes. Yes, okay. That's another way of looking at it. You can only change data over the length and sequence for a fraction D. Okay.
But that's only because you're choosing Hamming distortion in this case. Right? If you had some sort of metric on
Okay, but wait. So we'll get there. Hang on a second. All right, so here's my minimization problem, and it turns out if you assume very, very large databases, n much greater than 1, law of large numbers kicks in, and I can do all the cool things that Shannon did, and basically it simplifies to single letter optimizations. And here's the solution I want you to take away. There seems a lot of math here. Effectively, the output distribution is going to only preserve those inputs. So remember there's a random variable x. It has a set of values in its sample space. They all have different probabilities. It's only going to preserve those samples in the sample space that are above the Lagrangian that represents distortion. Okay? So in other words, every sample that has a probability below this lambda threshold will actually be suppressed from the output.
So you're not allowing an erasure option, right?
No. You don't allow for it. I mean, in this case, it's Hamming distortion, so you're not allowing for erasure option by definition. So this mechanism sort of comes out of the optimization problem, right? It's not something I'm imposing on it.
So lambda here is
Lambda here is the Lagrangian that you have when you include your distortion with your mutual information. When you minimize this jointly, right? Remember, it's a constraint, so you can put it up.
So when, like this is the same lambda in the Lagrangian and in the
That's right.
probability.
Right. So the lambda is such that this is going to be bounded by d.
Lambda is less than 1. Right. It's a probability.
That's correct.
We can interpret it.
Right. D is itself between 0 and 1/2 or 1, right? So.
And the choice of the different x, like in the second case you take, x had to be different from x. It could be like.
Okay, so let's walk through this, right?
It's like a deterministic choice based on that.
No. So let's walk through this. What you're saying, this is actually the reverse channel. So given x hat, what would x be if they are equal? It is likely to be equal with probability 1 minus d. They are unequal with probability lambda only if what you're looking at in your output, what you're looking at in your input belongs to the output set. So the broad idea here is that even though you allow for the space of all zip codes, the output space may not have all those zip codes in them.
Can you draw a picture maybe that would just water?
I'm going to get there. Bear with me for a moment. Yes, I do.
Have a chalkboards.
I do have a picture. But, all right, here's what we're saying. So this is our random variable x, and it's distributed as p of x. So x actually belongs to, say 1, 2, up to m. Okay? So if I plot p of x here, you have values 1, 2. These are the probabilities for the m values. Without loss of generality, you can even just do, you can just plot them. This is p of x on the x-axis. Hang on. Yes. So when you have a water level lambda, basically all these samples will get absorbed here. This is your input distribution. This is going to be your output distribution. Yeah, so I just plotted it out for those m values. These are not numbers, these are probabilities.
But I don't understand why there's a curve, because there's n discrete points, so there's like a center.
Okay, fine. I just put a line through it. I could have just plotted m points, right? Okay. Here you go. 1, 2, 3.
Just like, I'm very confused, so please help me.
Okay.
I'm actually confused about it. Like, it's not,
Okay.
I'm not trying to be a jerk here. I just don't understand.
All right, so you have m points in your sample space, in your input sample space. These could be m zip codes. So every zip code has a probability associated to it.
So the first one has very low probability.
The first one is very high probability, then,
The px is very small, right? Because p1 is close to 0.
no, this is how I'm ordering it.
Okay, so
Okay.
that's what I'm understanding.
So,
Is the x-axis actually x1? Is it 1 through n, or is it n that you're plotting on the y-axis of p1? Because otherwise we just reverse. If you just look what you've written on the axis here, you reverse the way it works, right? So infinity is at 0 here. And p1 is
okay, all right. I mean, so let's do, okay. All right, let's do it the other way. So I have to be a little bit careful because it's not an exact number on the other axis. Suppose you just had m points, so p1 less than equal to p2 less than equal to p3 up to pm. So these are the probability mass functions, right? So you have a water level lambda.
Again, now what is this height?
These are probabilities. Okay, so you could have said P1. Okay. All right. Okay, P1, P2, P3. I wanted to map it, but we don't have to do that. So when you have a water level, when you have a level lambda, effectively all these samples, maybe there's another sample here, that's below this level gets absorbed into these samples. So you never see them in the output.
So zip codes with small numbers of individuals will get deleted.
Yes, zip codes with so people living in some really rural county that are very few in number would be represented here. Or if it was race or something in a neighborhood, maybe the person who just stands out and is not like the rest, if you allowed for some more racial characteristics, something like that would be here. So effectively, you're removing the outliers relative to your distortion requirement. Okay? So, I mean, in that sense, this is very similar to what was at least done for the census database for a very long time, this notion of aggregation, suppression, and imputation.
I'm still, like, I understand I think I understand what you're saying here, but I'm still not clear I understand which optimization problem this is solving.
Okay, it's solving this optimization problem.
So this is, so the thing I'm minimizing over, is it over joint like over the entire, in your first slide, x hat was everything you send out. On this slide, x hat is one symbol.
X hat is a random variable.
I understand, but like there's an n, right? So here, are you assuming?
So there's
independent processing of each symbol?
no, you do not actually assume that. But what happens is that when your source is independent and when n is very large, you can apply a lot of Shannon theory to show that the optimal mechanism is really an IID mechanism.
I see. Okay, because somehow that doesn't come through.
Yeah, so this should have been x hat n given xn. That is a typo there. What happens is that when you go through the math of it, this just simplifies to this just simplifies to the problem of minimizing I of xn and x hat, I of x and x hat subject to a.
Next question. So you're asking, yeah, okay, I think I got it. Good, thank you. So xn, here you're saying talking about Hamming distortion, but here the optimization problem, the Lagrangian term is the probability that they're equal, that the Hamming distance is 0 or non-zero.
Yeah.
Which is different.
So when you have a Hamming distance for any pairs of input-output, and when you have an expected value.
Okay, so I somehow want to.
Sorry. No.
Hamming distance on vectors, to me, it means the number of places where the vectors disagree.
But that is exactly what it is. I mean, so, but we're just adding up for every one of those. But it is.
You've got sup n. So again, like there's some disconnect between the notation and what I'm understanding.
Okay, so so if you go back one more slide, the way we write things is really in expected values. So yes, Hannah.
No, I just want to say, I think I clear about Adam's confusion. It's the distortion. The distortion is defined for single x hat,
Mm-hmm.
and the extent filling then just by adding.
Right.
But the term says, like on the slide, it says the probability that the entire x vector is not equal to
n times d. Right?
So,
okay, but that's not what you wrote on the slide, right?
I defined this function for you.
Right, I got that.
Okay, and then the actual distortion that we want is really this sum of the it's a symbol by symbol distortion.
Right, and what you wrote on the slide
Average.
is probably that the two vectors are not identical.
Yeah, so then you can actually show that when it's 0, it has this cost function of 1 when they're not the same and 0 when they're the same. this just turns out to be this probability model.
That probability is not correct, right?
Yeah, it's actually a summation over.
So you're saying
That was my question.
Oh.
This is my question.
this thing, that probability should be replaced by this summation.
Right.
Okay, so it's a typo that when you wrote xn equals.
Okay, so it should be
x
this.
n hat, that's just a typo, right?
Thank you. Yeah. Okay, thank you for pointing that out. So do I need to go over this, or does this make sense? Okay, all right. So effectively, what I want you to take away from whether you buy into information theoretic privacy or not is that if you had a data set and you knew how it was distributed, and if you determined the optimal information theoretic mechanism, say for a distortion metric such as Hamming distortion, what you are effectively doing is suppressing the outliers relative to your distortion constraint. Okay, so the one other thing that comes out of this, statistically, you're preserving the utility while you're suppressing those who are the most easy to identify from the data. Okay, all right. So just broadly, state of the art, there has been work on looking at mutual information as a metric, and a lot of people know about this. And there's also a notion of worst case, and I'll talk briefly about it later. But in general, anytime you have an information theoretic approach, the problem is an optimization problem where you're minimizing a metric for leakage subject to a constraint on what you want for utility. Okay, typically quantified as distortion. All right, so here I write the data models to determine how the optimization problem is to be solved, and I'll talk a little bit about it. Do you assume a very large database? Do you assume IID models? Do you assume very small databases, and so on? And so we will go over that. So at the bottom of it, our models assume that the adversary knows the source statistics and knows the optimal mechanism that we compute. Okay? And so the state of the art in terms of information theory privacy can be broken up into 3 parts. And there's this asymptotic analysis that I sort of take a view on. And then there's this non-asymptotic analysis that you may have seen in Yi Wang's talk. And then this new work that I've been doing on fine asymptotic methods, because I think non-asymptotic, it's unclear to me how you can use it. Okay, so going really a long time back, it turns out Reed, as in Reed-Solomon codes, wrote a 2-page paper saying that, actually, see, this theory of rate distortion can be used to look at privacy of databases. We're talking 1970s. And then Yamamoto in the 80s had a model, again, very information theoretic, where he said, you know, we have video streaming in Japan. We want to reveal one part of the data, and we want to compress that data, but there's some correlated data that we want to hide. And very traditional mutual information-based metrics. All right. Since then, later, in terms of asymptotic models, so there's some work that I've done on this, where I say that we are looking at large data sets, and they go to infinity, and we have public and private parts, and we want to map the public while we minimize the leakage of other privates. And the privacy metric is really, on average, how many bits do you leak in terms of mutual information, and the utility is always this, yes? Thanks. Okay, thanks. I was going to get to that after this. So the utility is this sum of the distortions. So there are 2 ways to look at this problem. Either you have access to both the public and the private. It's as if you have access to some of the personally identifiable information. You can scrub it out, but you want to make sure what you reveal still doesn't leak anything about that. Or you may just have statistical knowledge of, say, somebody's political preferences based on the data you have. So in that case, what you really have is this statistical model where even you, as the curator of the data, do not know the private aspect why. But you have a statistical model for it. Okay. Is that make clear? Is it clear to you? With that?
Clear to me. I was just because I wanted to tie back since you weren't you're playing with SDA's talk. So you had this idea of output perturbation versus
Right.
sort of joint full data.
I will talk about it.
Oh, okay, you're going to talk about it.
Yes.
Because, yeah, I just want to get my hand.
Sure, I will talk about it. this kind of a problem where you have a privacy metric and a utility metric is really very, very analogous to what problems you see in rate distortion, which is really the theory of compression and information theory. Okay, but the difference comes about because what you are quote unquote suppressing in terms of privacy constraint is different from what you're trying to preserve in terms of utility. The privacy is on Y and the utility is on X. So oftentimes these problems are not easy to solve. But also you can use this model for streaming data, for correlated data, for a large, where you assume that the correlation is really bounded relative to the amount of data you have, and so you can look at it in terms of blocks, and then you can do some math there. So there's some work we've done on smart meter data, and effectively that's where I talked yesterday about saying, even though you have correlated data, you can map it to a kernel space. So for smart meter data, it sort of maps to a frequency space where you're again going to suppress those events that correspond to these very, in terms of frequency, the low energy components will get suppressed. The low energy components are typically the ones that, on the spectrum, are typically the ones that just spike up in the time domain. So they come for very short intervals of time. Okay. All right. One last thing I want you to take away is that when we assume the sources are IID, our optimization problem simplifies to a single letter from your n-letter expressions. You just get this simpler problem. And the optimal mechanism is a memoryless mechanism. What this means is that everybody who has their own data could be applying this mechanism.
Question, when you say the optimal mechanism, is that an exact statement for finite n, or it's an asymptotic?
Asymptotic.
And how?
I'll talk about finite in a moment.
I was just going to ask, do you know how?
I'll talk about all that.
All right.
How close it is, how it depends on n, and so on. Yes. We don't know all the answers yet. It's still research in progress. Okay, so keep in mind if you had a very large database and if people had the data themselves, or you could just apply the mechanism at one data at a time. Okay, so that sort of is captured here. Where should you apply the mechanism? Should you do it at the data provider versus the data collector? In general, if you had very, very large databases where law of large numbers could kick in, you can do it at the data provider. For non-IID and non-asymptotic, you really want to do it at the data collector, because now you have access to the entire data and you can design a mechanism for the whole data. You have a question, Cynthia? Okay. All right. So talking about non-asymptotic methods, what this is that you have a block of data, it comes from a distribution, you output a block of data, x hat n, and then it just, in the information theoretic model, it just becomes an optimization problem. And note here, I've tried to stay true to these works by writing x and y, but x and y here are just really vectors. Okay? Yes?
So, how much any of these results can things extend to continuous outputs versus having to sort of stick with discrete outputs?
You can. See, the problem in the non-asymptotic is you do not have any results for specific models. Right? I mean, you just write this optimization problem. What you'd have to do is go compute it.
Like find a finite block.
This is not finite block length. So I desist from using that, because if you look at the utility metric in all these papers, and these are very good researchers, including Yi Wang and Fawaz and Kalman and all that, they use an expected value, expected notion of utility. And I'll argue that when databases are small, expectation is not sufficient as a metric for utility. And I'll come to that in a moment. If you just looked at the simple optimization problem, you have n-length vectors, you're going to output an n-length vector, you want to find that mechanism that maps an n-length vector to another n-length vector, you would solve this optimization problem subject to this expectation constraint. All right? So this is not an easy problem to solve, but this is how this has been formulated. In this context, let me place Yi Wang's work in context. What he showed is that if you had a joint distribution on x and y, if you do not know y, the amount of leakage you can guarantee in general will be less than if you knew y. If you had only statistical information about y, you will generally guarantee less leakage. The mechanism cannot guarantee as much leakage as if you knew y, because then you can sort of separate it out in some statistical sense. Right? If n is really large in these models, because you have an expectation constraint, and if the source is IID, you just go back to the asymptotic case. All right, but here's what I want to leave you. When databases are small, the law of large numbers will not kick in, especially when you have a reasonable sized alphabet. So there is going to be a dispersion about this underlying expected value. You need to capture that with more than just the first order statistics. You need to go to second and third order. And so this is why you need what are called fine asymptotics. So fine asymptotics is something that's relatively new in the literature of information theory. These are harder. You don't just use strong law of large numbers. You have to use central limit theorem and Berry-Yassine kinds of bounds to do this. They're not easy. This is something that we have been working on for a few years, and it turns out to be a really not so easy problem to solve. So I still keep the same privacy metric, but here's how I define utility. My utility is the probability that my distortion will exceed some level that I keep for it, and I want to bound that probability. So there's a probability on the excess distortion. So the right way to look at this is to say that for a certain number of sequences, a fraction epsilon of sequences, I am going to let them exceed the distortion metric. So in other words, I will be publishing junk for those fraction epsilon of sequences from my source. A zero excess distortion will become expected value in the limit of very large n. Yeah, this is non-zero epsilon.
Okay, but can you do zero epsilon?
Zero epsilon only makes sense when n is very large.
I guess the question is, like, what does it buy you to allow this? Does it buy you a lot to allow this?
No, so what it buys you is that you're cognizant of the fact that your data is not going to exactly look like your underlying distribution. So there's some dispersion, and for these sequences that do not behave typically, you're allowing those non-typical sequences to be thrown in and said, we're just going to publish junk for these non-typical sequences.
So I think maybe one thing it's not.
So as n becomes larger, non-typical sequences become less, but n is smaller. It's actually hard to quantify bounds when n is
So
small.
this probability is over the source generation process X.
Yeah, it's over the joint distribution.
Over the joint distribution. So you're basically concerned about this epsilon probability that the source produces like all zeros for some reason, even though that's very atypical.
Correct.
That epsilon is allowing you to say, I don't care about that. Typical realizations at block n for modern.
Right. Yeah, so I mean, one can argue about what kind of metrics should work for small block lengths. Even that is sort of an open problem in finite block length information theory. And this notion of tail probability or excess distortion is just one such metric. All right? So effectively, the takeaway from the slide is that in addition to the first order, you want to look at some kinds of second order terms, dispersion terms that scale as 1 over square root of n. I'll get there. It's even harder than that. Let me walk through what we know now and what we can do. Okay, so let's step back for a second. In the asymptotic realm, this is how I define leakage when I have x and y. It's really minimizing the leakage between y and what should reveal y hat, subject to an expected constraint on the distortion, on the utility. Okay? And when you have a tail probability constraint, and if you look at, you force this. Keep in mind when you have finite block lengths, memoryless mechanisms will not be optimal. You really want to take your whole data and map it. Anytime you just take one element of your data at a time and apply the same mechanism, that is not going to be optimal. But you can consider that as an achievable, as some mechanism, right? So if you apply a memoryless mechanism, we just call that LM here. And now you have a dependence on n and epsilon in your expressions. So, and here I've replaced the expectation constraint by the excess distortion constraint. Ideally, the correct solution is to allow for all possible mechanisms, not just memoryless mechanisms, and then solve this problem. The reality is we haven't been so successful at it yet, and I'm going to step back for a moment and tell you some interesting things. If x is equal to y, we always go back to rate distortion. It's only very recently, like a year back, that the solution to this problem, when x is equal to y, has been solved. It's at what rate do you transmit if you allow for an epsilon fraction of probability that your compressed sequences have a distortion more than d. Okay? In that case, what happens is, here's the most interesting thing. You can compress below the Shannon theoretic limit. And similarly, you will leak below the Shannon theoretic limit on leakage. So 1 minus epsilon is the only fraction of time only fraction of sequences for which you're compressing or leaking information about. You're frowning. Oh, okay, asymptotic. Sorry, yeah, first order. Asymptotic. I mean, this holds true only when you have these second order terms and so on. Mm-hmm. Correct. So in fact, you go below and this luxury comes to you because you're allowing yourself this error. Shannon theoretic asymptotically, 0 error, right? Okay. So what is this term here? This is actually the var entropy. It's actually the dispersion of the information. I won't say more than that. I'll just leave it at that. Now, if we restrict ourselves in the x, so we can also consider this case of x is equal to y. We only have one database, and we can look at memoryless mechanisms, and this is what we get. Keep in mind, this is not optimal. This is optimal. And this was already solved, yes. This is already solved, and we didn't know about it. We actually did this work, and then we found out about it. Okay, but we still put that in there. And really, this term, as in here, involves the first order derivative, the first derivative. Okay? All right, it should be minus there, huh? That's a different result, and that's zero excess distortion. That's for. Yeah, but we're not talking rate distortion there. Contianus's work is on error-free compression, but let's not go there. Yeah, afterwards. Yes.
Sort of I think a higher level question, which has to do with the type of distortion functions you consider. So the example you gave us to keep in mind was the one that's on the board.
Yes.
Sort of this average over the probability that I reproduce a given data point exactly. And obviously, if I can get that probability to be high, somehow magically subject to good privacy constraints, then that's great.
No, you want it to be low.
The probability that they'd be equal, if I can somehow make
they'd be
high,
equal. Okay.
Like if I can get the disagreement probability low, that would be fantastic.
Right.
Although, for reasonably interesting data, I would, you're generally going to get any kind of strong privacy constraint. This probably a disagreement itself will be high. Right? And so, if you look at the literature that I'm more familiar with, people have sort of looked at kind of more operational notions of utility, like how well does this allow me to do certain things, like compute certain statistics about my data, maybe estimate the empirical distribution of the underlying data set,
You could,
things like that.
you could do
so
that.
The question is, how much of first question is how much of the general theory applies to distortion functions that are kind of higher level, like talk about the data set as a whole rather than individual symbols. And then secondly, how much of how many, and like even if the sort of theory applies in general to those sorts of types of distortion functions, can you say anything specific about interesting examples like that are not these kind of
symbol-wise, yeah.
Symbol-wise.
We know less about block distortion, but we know it for specific things such as estimation error or probability of errors. And I'll show one example a little later by Kalman that was looked at. But rate distortion by itself is still an open area in that we have an optimization problem. We can always go solve it. It's a convex optimization problem. But we don't have closed form analytic solutions for a large set of, anybody can and contradict me, but it's true, a large class of sources and a large class of distortion functions.
Okay. One thing, way to address one part of Adam's question, I think, is that here, since you assume that you know the source distribution, any question you want to ask about the population, since you know the source distribution for a large n, for asymptotically large n, right? You don't need to do anything. You don't need to look at. You don't need to have any view of the data, right? I don't need any x hat. I know the sources IID Gaussian with mean mu and covariance sigma squared. So I know mu and sigma squared. Who needs data? I've estimated everything I need to know about the population.
So actually, this gets at a
Statistics.
a different issue that I don't want to hijack too much of your time, but there's these underlying probability distributions. They represent like two fundamentally different things that are often conflated. One is how much an attacker knows about the data ahead of time. That's the distribution you use when you're modeling privacy. And the other is how much the legitimate user knows ahead of time, which is presumably a lot less, and that's the distribution you should use when you're modeling utility. And there's good reason to make those two distributions completely different, meaning you should assume, it makes sense to assume a user knows relatively little about the data because they're the one who's trying to learn something, whereas an attacker maybe has lots of side information and knows a lot.
You can extend your model to partially incorporate that. So you can take a max over a family of channels from a super.
It comes.
Which will capture.
Right, it comes a little later. But I think he's making a more nuanced point. He's saying allow the adversary to know the exact distribution of the data.
The model for the adversary information should have some family which models his knowledge.
Yeah. So we do that. So you can go towards more and more universal views of this. The problem gets harder and harder in terms of getting closed form expressions. But these bounds are ways of starting to look at the problem. Okay? And all right, so what I wanted to go from here was, okay, we know how to do memoryless. So the question is, if you had X and Y and you still wanted to do this sort of finite size databases, if you rewrite this problem as this optimization problem that I talked about, the Lagrangian, you get those complex things. The takeaway here is that you again get what is called a detilted information where you would waterfill on this function in some sense. You get very similar to this, but we haven't been able to go from there to prove what we conjecture for a general mechanism where you're mapping the whole data sequence to an output sequence. You should get, again, this decrease by 1 minus epsilon, and you should get a second order term that's negative, and scaling is 1 over square root of n. We can either get this or this. We haven't been able to find a mechanism that puts it together. But to give you just a little clue about, to give you a little clue about what's happening here is that effectively what you're doing is you're only preserving those sequences relative to the output that satisfy distortion, and the rest are thrown away. And that's how you get the 1 minus epsilon. Okay? But when you have X and Y, it's much harder. All right. So that's all I will tell you about. Yes?
So I just wanted, operationally, if I thought about the mechanism that you're proposing here, you're saying, okay, if the X is atypical, doesn't look like it's IID according to the unknown distribution T, you'll just say, I'm not going to report anything. You might as well just say.
That's right. So it's an epsilon, sort of an epsilon delta, but it's actually in the opposite way that you actually reduce leakage because you just say, I'm not going to report anything. No way. Okay, I'll just multiply it by 3. No, I'm halfway done. In the second half of the talk, we'll talk about composition. So how do we even talk about composition here? I'm going to take a general framework where there's 2 agents and they want to share data with each other, so they go back and forth and back and forth. So these are rounds. So the one to other in multiple queries just becomes a special case. All right. So this also borrows a little bit from the rate distortion literature, but here's where we are different. Now we say that we have these public and private data at each agent. These could be 2 people in the power grid. right? Two control centers in the power grid. They want to share these X's with each other, but they want to make sure the X's do not reveal as much as possible about the Y's, right? Which they themselves do not know, actually. They have to compute it from the data. All right, so we assume a Markov relationship here between Y, X, and whatever you reveal. Now, with it, at every iteration or every round, you're going to have a mechanism that maps your data to something intermediate. And in the return round, this agent will use all its own data, whatever it has received from the other agent, and then compose a mapping. Right? So this is how you get K mappings. So with each agent communicating K over 2 times. And as I said, I think I've covered most of the things here. So there's
These mappings are chosen
randomized
time
mappings.
or
No, so the mappings are chosen to satisfy these constraints. And here again, you will see that these are asymptotic, so I assume that it's a symbol by symbol average distortion constraint, and I want the leakage about my private from all the things that I've revealed and all that you have at your end to be bounded by some number.
So after K rounds, we make an estimate, we form an estimate, and that's how we pay for distortion. So we pay for distortion only after.
Yes, you pay for both distortion and leakage, so you will compute ahead of time if you knew what K was, what the mechanisms for each round will be. But keep in mind the mechanism for each, it's a causal system in the sense that you determine your first mechanism and determine the second mechanism after the first. So the first doesn't depend on the second, third, and so on. Okay. So in that sense, you could do it even if you didn't know K, but you just have this total privacy budget and a total distortion budget. Right? Okay, so what we have here is that, if you have asymptotics, you can simplify this to single letters. You have all these results, and what I want to show is the following, is that interaction can help reduce leakage relative to a one-shot data sharing. And this is not true for all sources. In fact, my next slide will show you when it's not true. But it is true for a large class of sources that satisfy certain properties. And that completely depends on the sources and their joint distributions. And it's a very complicated proof. And effectively, what you take away from it is you can compute these sums for any number of rounds, and if these sums converge very quickly, basically or it converges the first time itself, or if 2 rounds have the same sum, then you're done. You do not have any more leakage. One shot is enough. Okay, so the point I want you to take away is that you could do better in multiple queries than in one query. Right. Okay, so it turns out if you had Gaussian sources and you had a mean square distortion, or if you had log loss distortion, then one shot is sufficient. You can do no better by sharing multiple times. Yes, Anna?
One back and forth.
Yes.
So
But
has that 2 messages are almost optimal kind of thing, sort of like that.
right. It's slightly different from that. It just says that for agent A to achieve distortion at agent B, there's just one round. For agent B to get distortion at agent A, there's another round.
But the message coming back is still dependent on the first message, or is it not? Are they independent?
It will be independent.
Oh, okay, so 2 simultaneous messages.
Yes, correct. It will be independent.
There's no rate loss.
That's correct. This is basically Weiner's if there's no rate loss when you have side information for Gaussian, right? Even if you're only statistical side information. Yes. Yeah, but yes, it's just Weiner's when you have only X, but if you have X and Y, it's slightly different. But it's a generalized Weiner's. Okay, so here's my composition theorem. Basically what I'm saying is that if you had K rounds and you had a total privacy budget, you do not lose anything as long as you design the mechanism in each round to be cognizant of all the data sharing that's happened before this round. So then the properties of mutual information, the chain rule, just falls in place.
And so what does this mean? It means you can do your optimization for the first round, then
Yes.
do your optimization for the second
Correct.
round, and so on and so forth.
Correct.
So this means that you cannot design your mechanism ahead of time, because you have to see what happens.
Yes. Yes.
Or I
But
guess-
but statistically,
Mechanism can solve some complicated optimization.
yeah, yeah.
If that is the case.
If that's the case, unless it's solvable analytically.
there's this assumption that you kind of had right at the beginning of the talk that you didn't talk about at all, which is the fact that like everybody involved knows the underlying distribution of the data set.
Okay.
And this comes back to, yeah, sorry, that's your timer. But this comes back to Anand's point that if you know everything about the data to begin, I mean, if you know everything about the data set to begin with, you know, how much more are you getting at? Like,
You're getting an instantiation of that data,
why
right?
is it reasonable to assume that you, the designer of the algorithm, know as much about the data as the
Adversary.
adversary?
It's a model. But I mean, if it's public information, if it's such as the census data and everybody knows, why would the adversary know more about the census distribution than the people who curate the census data?
Well, because the adversary might know an individual. Like, it depends what you mean by.
Yeah, but that's site information, and you can quantify site information in all these models.
If you know what it is.
You can have statistical models for site information.
Will be available in the future.
Yeah, I mean, composition, in any model of privacy, if you do not know ahead of time what the site information that the other person has, it's not clear how you could fit to that model.
Well, that's exactly the kind of thing one.
I
you
think
know,
the census analogy might be like the wrong one. Like think about the grid applications, right? You have loads on lines, right? That's it. Like loads on different power lines.
Mm-hmm.
You know, you might have very good statistical knowledge from like longitudinal observations of these
Yes,
power lines
in fact,
for
you
a
do.
long time.
Mhm.
But what you need to do is report last week's actual realized load on that line.
Or
You
today's.
really have a very good sense of, and everybody has a very good sense that it's generally speaking
Gaussian.
Gaussian.
But it can change if a line has fault, and it happens all the time.
But you have to share some number, so you have to send something to the other provider, the power provider, right? So it's not, it's different.
All right.
I just want to like point out that the idea that the adversary or everybody has statistical knowledge of the thing, but not the realization isn't entirely unreasonable in several applications.
It's particularly true if the data size is small. Right? Okay. He's not buying into it, so I'm going to move on. Here's an example. If you take the U.S. Census data, I mean, it's actually, this is the from the UCI database. You can actually use log-loss distortion, and I'm going to very quickly go over this. And effectively, if you plot what you get as a leakage for 1 round versus 2 rounds, you can actually do better in 2 rounds. All right? We'll talk all the details later. So I want to leave you with one slide on what does mutual information theoretic privacy get you. And that is really, I think it can allow you to quantify fundamental bounds on inference, which has to be defined very correctly. And conversely, on if you had a data set with a particular joint distribution of the public and the private, how much really privacy can you guarantee if these two are highly correlated? Not taking statistics into account will never tell you that in some sense. All right? So there's been some recent work in saying that you have this private data. Suppose you wanted to minimize the probability of error of estimating this data. It turns out the joint distribution of the data tells you exactly what the bounds on this error probability are, what the lower bounds on this error probability are. Okay? So if it's highly correlated data, that bound is going to be really, really low. All right. And then we're also looking at bounds and classification, and in terms of like hypothesis testing. No time to go into it. I just want to leave you with one more thought. There's been work which has actually come from the computer science community, Alvin et al., who have looking at worst case average case. So when you have this joint distribution of x and y, you do not really know why. Can you look at the worst conditional distribution of y given this x, the public, and then talk about worst case mutual information? And there's some interesting things there, but it's very nascent work.
Still mutual information.
Yes.
But worst case over one of the distributions, not worst case over sort of realization.
Yes. Right. So I mean, so in some sense, you're saying you do not know how they're distributed. You're going to look at the worst distribution. Okay. You can design for the worst distribution. I want to leave you at last with just a few slides on how can we compare IT and DP. So here's a very simple model. We're going to look at n data points. They come out of a distribution. I'll say that later. What we want is to reveal x hat n. And so we want to design a mechanism, but we also want to make sure there's some notion of distortion between the two is bounded. Okay? All right. So I'm not even going to go through this. Basic differences between these two are that here there's an assumption on the underlying source statistics. There's really none here. And here there's the source statistics is used both for privacy as well as utility. Here you could use the statistics for utility. At least we do in our comparison. So how do we compare these two? So what we did was we said, let's assume that in both cases, there's some knowledge of the statistics, but it's not precise. So the sources fall in a class. And then what we also assume is that both of them now have to satisfy the same utility constraint. All right? Okay. You know the stuff. What we use here as a differential privacy metric is really, which he doesn't like me to contribute to Ducci, is the local privacy model. In other words, there's no difference between x and x hat, but what I meant is, I mean, it has been done before too as well. So what we're saying here is that.
Yes, it was. It does predate the 2012 paper of Ducci. Yeah, it appears, for example, in fact, the term local privacy comes from, circa 2007, 2008, but it predates even the definition. The differential privacy paper, equivalent notions were defined
By Warner, as you pointed out.
2003, very explicitly by Johannes Gericke, and then this sort of gamma amplification thing. But even this term, local differential privacy, predates Ducci's paper by 4 years. And if you read Ducci's paper, it's very clear that they don't say they're defining this model. They attribute it to previous work.
Okay, all right, I'll keep that in mind. So basically what we're looking at here is we're saying that instead of just looking at differential privacy for two data sets that are different in one neighbor or the nearest neighbor, you are allowing for all possible inputs and then looking at the ratios over all possible input pairs for a given output. All right? Okay, and so then we have a set for any epsilon dp that allows for all mechanisms. Okay, so this is also known that the worst case differential privacy guarantees average case mutual information bounds. So what can we say beyond that? And here's how we try to compare the two. We allow both of them to have source statistics, and so our distortion is at -1. Our distortion is this notion, and then we're looking at the worst case. All right? So we're going to find the best mechanism that gives you the worst distortion for any source. Okay. And so the two ways to compare is you fix distortion and look at privacy and vice versa. And what I want to say here is skip. We looked at two different kinds of source classes. And in the process of really comparing the two, we started looking at how do we find optimal DP mechanisms, okay, under Hamming distortion. And what we came up was, we looked at these two source classes, which are permutation invariant and sort of ordered statistics. And what we can show is that the staircase mechanism is optimal for permutation invariant. Okay, I am going to go back for a moment. We did this with a binary case. We restricted the source class to be between some min and max, which is bounded from 0 and 0.5. What we showed here is that there is a discontinuity in your epsilon dp at the maximal probability of the source class. And what is happening here is that at that maximal probability, basically you collapse to one output. So anytime you have this collapse to one output, reduction in support, we suspect that there will be a singularity. We haven't been able to completely verify it yet. So what we have been able to show is that for permutation invariant, we can find the optimal mechanism under Hamming distortion. And then if you had a ordered statistics, this is what I want you to take away. Forget all the math here. If you had ordered statistics and you are looking at a class and you're looking at minimize or the distortion over this class, effectively, as you increase distortion, you get these points just like you get here in information-theoretic privacy, where your support set reduces. Okay? And we have some bounds. We've not been able to show it. We can show it for certain ranges of the distortion. All right? So I will leave you with the following conclusions. I think information theoretic privacy can be useful in the context of inference problems and where statistical utility has to be guaranteed. And it'll be interesting to understand fundamental bounds on inference and that can be provided by these kinds of impossibility results, in other words. Okay, thank you.